Okay, now look at the second lecture note. So the classical linear regression model, so as mentioned before, the model can be written using this equation. So we have dependent variable and then we have the independent variable. We have n-intercept plus all the independent variable with each of the independent variable. So there is what we call the slope parameter attached for each of them. So where yi is the ith observation on the dependent variable y, so beta j is the coefficient on the jth explanatory variable or regressor xji, and the ui is the ith observation on an unobserved error term u. So they are n observation and k regressor. So we have up to k regressor. So we have x1, x2, up to xk, and n observation. So for each of these, so we have y1, the first observation, y2, second observation, up to yn. Similarly for x1, for example, the first x1, 1, and the second observation x1, 2, and up to x1, n. And the error term u1, u2, up to un. All n observation in the model can be written as a set of equation. Okay, so for each of the observation, the first observation, and then we have this equation, and then second observation, and so on. So if we have large observation, then you can write down the equation for each of them one by one like this. So, but if you have large observation, then it's not a convenient way to write down the equation for each of the for all observation. So this system can be expressed succinctly using metric notation as given by this. So you can express your data in matrix form like this. So you have a vector representing values for your dependent variable y1, y2 up to yn, and then you have a matrix of x that has inside the x it has the what we call that the values for all x, x1, x2, x3 up to xk, but in the first column it has all equal to 1 because if you have intercept in the model and intercept, then you need to have all the first column all equal to 1, so that when you multiply this and this, and then you get back this equation. Now you have beta 0 plus each of these, and then you have a vector. So this one a vector for your parameters, the slope parameters, including the intercept. In the set and slope parameters, and then you have a vector for the error term or disturbance, or this equation can be expressed using a symbol like this. So so your vector for y, you just use this one y, and then equal to x, matrix x times the vector for parameters beta plus the vector for the error term. Okay, so previously I explained to you that we're going to use this method to estimate parameters, the ordinary least square estimator, or OLS. So let be an estimator of the unknown parameters. So these are unknown parameters. So let's say we have a vector for the estimate. So we either use the symbol B, or we just simply put beta, we put hat on this, so beta hat. Okay, so that instead of this equation, you can just rewrite the equation to be, or express the equation for the estimate, estimated values to be this one. So this one, our estimated equation plus error term from sample, the estimate of the error, or we call it as a residual. So this is a vector containing residuals. Residual is an error term we produce from sample after we estimate. So where E is n times 1 vector of residual, they are not explained by the regression. The ordinary least square estimator, beta hat is the estimator, B that minimize the sum of square residual I already explained before. We want to find the estimate of parameters that will give us the smallest sum squared of error, or after we estimate, so the sum squared of residual. So in this case, this is a vector. This one E is a vector. So it has E1, E2 up to EK, the vector of residuals. So to get sum of the residual, okay, the sum of residual, you can just multiply the transpose of the vector E and E, the vector E, so to get this one. Okay, so E transpose E, so meaning that you have a vector, so in tips E is a vector, is a column vector, so that E transpose, it becomes a row vector like this. So times the column vector of E. So this times this, so we have E1 square plus this times this one, so plus E2 square and so on. So it is equal to the sum of all squared of the residual. So sum of the square residual. Okay, so again, we want to find the estimate of the parameter that will give us the smallest sum squared of the residual. So that so this one E transpose E is equal to, so meaning that because so this is the error, so error equal to y minus this one. So y minus xb is equal to the residual vector for the residual. So you multiply this one, so you get sum square of residual. So this times this one. So you, or expanding the last expression, this one, so it's equal to this one. Okay. And then, so previously I mentioned to you that we want to find the best line that gives us the smallest sum squared of residual. So you do not need to do to what we call it, to manually draw each of the possible line and then find which one has the smallest sum squared of residual. So you can just use what we call as the derivative, the method of derivative or differentiation, in order to find what are the values of estimator, the values of estimate for the parameters that will give you the sum, the what we call that, the smallest value of sum squared of the residual. So this equation, if you use the techniques of derivative differentiation. So you take the first, what we call it, the first derivative, so delta S over delta B. So you get this one. So because this one you don't have B, and this one because there is one B, so it becomes negative 1 transpose X. This one also you have 1B, so it is minus X transpose Y. So these two, you get Y transpose X after you perform derivative, the first derivative, and then this one minus X transpose Y, so it's equal to minus 2X. I mean, it is equivalent to the, or is equal to the negative 2 times X transpose XY. And then this one we have, there are 2B. Okay, so just like B square. So you perform the first derivative, so it is 2B X transpose X, or this one, so 2 X transpose X B. Okay, so if you solve this one, so you make it equal to 0. So you solve it, you get the smallest. You get, you solve it, you get what's the value of B that you give it the smallest value of sum squared of the residual. So you rearrange this one, so you get this, and then on the assumption that the inverse matrix X transpose X inverse exists. So multiplying the above equation by X transpose X inverse give the expression for the OLS estimator. So this one you multiply each of the two sides with X transpose X inverse. Okay, so we cancel this one. I mean, we can cancel out because we divide this and the inverse. Okay, so cancel, we get B, and then this one X transpose Y times the X transpose X inverse. Okay, so this is the solution, the equation for us that can be used to find the set of value of estimates for the parameters that will give us the smallest sum squared of the residuals. Okay, so meaning that instead of you draw the straight line one by one in order to find the best line that gives us smallest sum squared of residual, then you just need, you actually can define the answers or to get the estimate of the best estimate just using a derivative Okay, this one through this technique. So this is the solution, the equation. After you express your data in matrix form, then you can just use this equation in order to find the estimate for the all of the parameters. Okay, so there are a number of assumptions or requirement for the model to be valid. So assumption means that the model must justify each of these so that the model is a valid model. Otherwise, the model is not valid. I mean, the model is not valid, so it cannot be used because it violates assumption or the requirement. The first one, linear regression model. The regression model is linear in the parameters, though it may or may not be linear in the variable. So the parameters must be, the model, that it must be linear in parameters. So meaning that for each of x in the model, for what we call that, for whatever value of x, when the value of x increase, the effects of the change in x will be the same on y. So let's say x1. So you have x1. When x1 increase 1 to 2, and when x1 increase from 2 to 3, then the effects of the, when x1 increase, it will give the same effects on y. Doesn't matter what's the value of, doesn't matter the x increase from what value to other what value. So that's what we call as linear in parameters. So if let's say you have a situation where let's say x1, when x1 increase 1 to 2, y increase 1 unit. But when that particular x1 increase 2 to 3, but y increase 2, so different, the effects become different. So that one we call as not linear in parameter. So in that kind of situation, so the regression model is not linear in parameter. So linear in parameter, again, it means that the effects of when x increase or decrease must be the same. It doesn't matter what the value of x increase from 1 to 2 or x increase to 2 to 3 or 3 to 4, the effects of the when x increase must be the same on y. They cannot give different effects, so that if what we call that different effects, then it is not linear in parameters. Then second one, fixed x value or x values independent of error term. Values taken by the regressor x may be considered fixed in a repeated sample. So it requires that x must be a fixed in the repeated sample. You perform sampling at different points of time. You repeat the sample, the sampling. You redo the data collection, and then values for the x must be the same. You cannot. If it cannot be different. The first what we call that data collection, later on when you repeat the data collection, it must be the same value. It cannot be different values. So that's the requirement. And then the third one, zero mean value of disturbance. So given the value of x, the mean of expected value of the random disturbance term is 0. So the average, okay, the mean or average of the error term must be 0, as mentioned before. What we call that the error term can be positive, can be negative, depending on the value of y and the predicted values. So which one is the higher, which one is the lower, smaller. So it's possible, the error can be positive, negative, but the average of all error must be what we call that equal to 0. And then next one, homoscedasticity or constant variance of the error term. The variance of the error or disturbance terms is the same regardless of the value of x. Okay, so the variance of the error. So you refer back to this one. So the variance of the error for this one, let's say for the first part of the error term, the variance of this must be the same for the other parts of the vector for the error term. So we call it as homoscedastic error term, or we call it homoscedasticity or constant variance of error. And then the next one, no autocorrelation between the disturbance. So given any two x values, xi and xj, the correlation between any two ui and uj is 0. So, okay, so it requires that each of these error term to be independent. They can, I mean, it cannot be correlated each other. So any of the error term cannot be related or correlated to other error term. So no autocorrelation or no relationship between different values of different points of the error. And then the next one, the number of observation n must be greater than number of parameters to be estimated. Okay, and then the nature of x variable, the x values in a given sample must not all be the same, no outliers in the value of x variable. Okay, so it requires what we call the x to have a variation in the values. Let's say you have a variable x, all equal to the same value, all equal to, I mean, the first observation equal to 10, second observation also equal to 10, up to the last one, all equal to 10, then you cannot estimate. You cannot estimate, you can, because the use of we use econometric model to measure the what we call that when x increase or decrease, how it influence the value of y. If x all equal to the same, consider of the same value, then how we can estimate the effects of x when x increase or decrease on y. Okay. And then the properties of least square estimator, you can refer to the main textbook for more detailed explanation. So n estimator is said to be a best linear unbiased estimator if the following holds. The first one, it is linear. There is a linear function of a random variable such as the dependent variable y in the regression model. Okay, so previously already I explained to you what what we call that linear in parameters. So it requires what we call that model must be linear in parameters. Okay, and then it is unbiased. That is average or expected value is equal to the true value. Okay, so unbiased, I also explained before. So it means that the average of all possible estimate we get from different sample must be equal to the true value of the parameter, which is the one that we see that we do not know, the unknown. But the estimator that can what we call that can give us the actual value for the average of all possible estimate, we call it as a unbiased estimator. Okay, number 3, it has a minimum variance in the class of all such linear unbiased estimator, and unbiased estimator with the least variance is known as an efficient estimator. Okay, so the Gauss-Markov theorem says that given the assumption of all of the classical linear regression model, the least squares estimator in the class of unbiased linear estimator have minimum variance, that is, they are best linear unbiased estimator or blue. So in this case, if the model, okay, if the what we call that the model and all of these variables satisfy all these requirement or assumption, then according to the Gauss-Markov theorem, it says that the model, the ordinary least square estimator for the model have minimum variance. The estimator for beta 1, beta 0, estimator for beta 1, beta 2, and so on, the slope parameters have minimum variance so that they are best linear unbiased estimator.